Welcome to Module 6, Data Link Layer. This picks up right where Module 4's physical layer left off. Now we cover how frames actually get placed onto that physical media and addressed correctly. Frame it as the layer that turns raw signals into something a NIC can actually recognize and act on. Objective: explain how media access control in the data link layer supports communication. Preview the topic table on screen. Purpose of the data link layer, topologies, and the data link frame itself. This module is the direct bridge between the physical cabling from Module 4 and the addressing concepts from Module 3. 4 jobs of the data link layer. Layer 2, shown on screen, enables media access. Upper layers don't need to know what media is used. Encapsulates frames, accepts layer 3 packets, wraps them into frames, exchanges frames, controls how data goes on and comes off the media, and detects errors, rejects corrupt frames. This is NIC-to-NIC communication specifically. IEEE 802 splits layer 2 into 2 sublayers, shown in the diagram. LLC, Logical Link Control, IEEE 802.2, sits between upper layer software and hardware, identifying which layer 3 protocol is in use. MAC, Media Access Control, is implemented in hardware itself. 802.3 for Ethernet, 802.11 for WLAN, 802.15 for WPAN, handling encapsulation and media access. Every hop a packet crosses can look different. An Ethernet LAN has many hosts contending for access, while a point-to-point serial link between 2 routers needs none of that complexity. At each hop, a router performs 4 layer 2 functions in sequence: accept the frame, de-encapsulate it, re-encapsulate into a new frame type, and forward it, shown in the diagram. A router commonly switches between an Ethernet LAN interface and a serial WAN interface this way. Unlike upper TCP/IP layers, data link protocols generally aren't defined by RFCs. Instead, engineering organizations handle physical and data link layer standards. 4 bodies shown on screen: IEEE, ITU, ISO, and ANSI. Students already saw these names in Module 4's physical layer standards. Same organizations, different layer. Physical topology versus logical topology, contrasted on screen. Physical topology is the actual physical connections and device locations, which room, which rack. Logical topology is how frames actually move node to node, the virtual connections, IP addressing scheme, and what influences framing and media access control. The data link layer specifically needs to understand the logical topology. 3 WAN physical topologies shown on screen. Point-to-point, simplest, most common, a permanent link between 2 endpoints. Hub and spoke, a WAN version of star. A central site connects to branches, but branches can't reach each other directly. And mesh, every device connects to every other. High availability, but high administrative and physical cost. A hybrid mixes these, like a partial mesh. Deep dive on point-to-point. The 2 connected nodes don't share media with anyone else, so with a protocol like PPP, a node doesn't even need to check if an incoming frame is meant for it. There's nowhere else it could be going. Note the callout. Point-to-point over Ethernet is the exception, since Ethernet still requires a destination check even in a 2-node link. Most modern LANs use star or extended star topology. Easy to install, scalable, easy to troubleshoot. 2 legacy topologies also shown. Bus, all devices chained on one line with terminators at each end, common with old coax, and ring, devices connected in a closed loop, used by legacy FDDI and token ring. Students won't encounter bus or ring in modern networks, but should recognize them by name. Half duplex means only one device transmits or receives at a time on a shared medium, used by WLANs and legacy hub-based networks. Full duplex means both devices transmit and receive simultaneously, the default for Ethernet switches, falling back to half duplex only when connected to a hub. Critical point: both ends of a link must match duplex settings, where a duplex mismatch causes latency and inefficiency. When multiple devices could access a network at once, 2 ways to manage that: contention-based access, all nodes compete in half duplex, only one sends at a time, CSMA CD for legacy Ethernet, CSMA CA for WLAN, versus controlled access. Each node gets a scheduled turn, deterministic but inefficient, used by legacy token ring and ArcNet, effectively obsolete now. CSMA CD walkthrough, shown in the 3-panel diagram. PC1 checks the medium is clear and sends a frame to the hub. The hub receives and regenerates the frame. The hub blasts it out every port, and only the actual destination device accepts it while others ignore it. If 2 devices happen to transmit simultaneously, both detect the collision, discard the corrupted data, and both resend. This is legacy hub-based Ethernet specifically. Switches don't need this. CSMA-CA is WLAN's approach, 802.11. Since wireless devices often can't reliably detect collisions the way wired devices can, they avoid them instead by announcing ahead of time how long they'll need the medium, so other devices know to wait. After sending a frame, the receiver sends back an acknowledgement confirming arrival. Note switches don't need any contention-based access at all, since switch-to-host links are full duplex. Every data link frame has 3 parts: header, data, and trailer. The trailer is unique to this layer, no other layer appends one. There's no single universal frame format. More fragile media like wireless need more control information, so their headers and trailers carry more fields than a simple wired frame would. 6 common frame fields, shown in the table. Start/stop flags mark frame boundaries. Addressing, source/destination on the local media. Type, identifies the layer 3 protocol inside. Control, special services like QoS. Data, the actual payload. And error detection/FCS ACRC check confirming the frame arrived intact. Not every protocol uses every field. Layer 2 addresses sit in the frame header, usually right at the front, so a NIC can check for a match quickly before processing the rest. Key contrast with Layer 3. Physical addresses are flat, not hierarchical. They don't indicate what network a device is on. They're tied to the device itself, and don't change if it moves networks. But Layer 2 addresses only work within the same shared local media. Different frame types for different media, shown on screen. Ethernet/802.11 for wired LANs and wireless respectively, cost-effective for high-density smaller area networks, PPPHDLC as common legacy WAN protocols, and frame relay ATM by 0.25 as older WAN protocols for various topologies, all increasingly being replaced by Ethernet even in WAN context now. Full picture, shown in the multi-hop diagram. As a packet travels host to router to host, it gets wrapped in a brand new data link frame at every single hop, with source/destination MAC addresses specific to that one link only. Meanwhile, the IP packet's source and destination addresses never change across the entire path. This is the Layer 2 versus Layer 3, addressing distinction from Module 3, now applied concretely to framing. Close the module walking each bullet. Layer 2's job is NIC-to-NIC communication and preparing data for the physical network. IEEE 802 splits it into LLC and MAC sublayers, physical versus logical topology and the common patterns. Point-to-point, hub-spoke, mesh, star, bus, ring. Half versus full duplex and mismatch risk. Contention-based access. Contention-based access. 20 MAC addresses changing hop by hop while IP addresses stay constant end-to-end.